Okay, thank you very much for the introduction, and also thanks to you all for coming here this early on a Sunday morning. So as we've already seen, the title of my presentation today is how to combine tiny bits of Python, physics, and art to create, hopefully, pretty pictures. And before I get into that, okay, now I have the same problem. So let's just use this here. Before I get into that, let me just tell you something about myself. So I'm a former scientist. My background is physics, just in case you have wondered, judging from the title of the presentation. I am a former scientist, but what I'm still a huge nerd and a lover of sci-fi and all things free and open source. And I think this is a really nice opportunity to speak about some of the things here this morning. What is maybe a little bit more disconcerting about myself is that I've worked not in one, but in two separate chemical engineering departments during the course of my career as a scientist, despite not knowing anything about chemistry. And I thought, okay, that's just such a good idea because I now work as a software developer, as a data scientist, despite not knowing anything about computer science and programming and all that nonsense. Okay, with that out of the way, let's start with an easy, simple question. What is this all for? And I think a good way of introducing this is this comic from XKCD, which I really like. There is this woman, she's probably a software developer working in some IT role, and she has this problem. She says, and the issue says, the recent update, it broke the software or the hardware support, the support for the hardware I need for my job. And of course, there's an easy workaround. The workaround is if you wait long enough, the Earth will eventually be consumed by the sun. And then so the problem will solve itself up. So yeah, that's definitely one way of looking at it. But still, if we're in the context of writing some computer program, we always have to ask ourselves, why are we doing this? And there are many various reasons to do that. Some which are often the case are, for example, some business interests. And we always know the business interests, they are always 100% legit. This is all good. You might even want to write a computer program to answer some super important and insightful scientific question. That's also interesting, I guess. But then every once in a while, something else is going on. It's not so clear, or maybe it has not this strictly defined purpose or reason. And in what I'm going to tell you today in my presentation, very much something else is going on. Now, in my particular case, this something else was actually inspired by art. A couple years back, I was in Switzerland with a friend. I was at this exhibition somewhere, and one of the things I saw there were these quite amazing paintings by the British artist Bridget Riley. They look something like this, and I'm not even sure if this is the exact painting I saw in the exhibition. This is just one I got from Wikipedia, which should be fine, copyright reasons and all that, And if you look up on Wikipedia, you will find some biographical information, of course. You will also find that she's famous for these op art paintings, which is just a fancy way of saying optical illusions as art. And pictures like this, or paintings like this, I should say, this is something which she does. And of course, she did a lot of things, but among many things, she did this kind of work. And I found this really fascinating. I like the shapes. I also like the colors a lot, how the colors interact with each other and how they really somehow play together. And I thought, yeah, that's cool. I like this a lot. But then I also thought, okay, maybe, just maybe, I can use a computer and create something which vaguely resembles this. So let's give this a try. And what I first did was I actually started just sitting down and doing some sketches in my notebook, just drawing, pen and paper. And what you're seeing here, this is actually not something which I made specifically for this presentation. This is just an original scan from my notebook. So all this computer stuff and writing software and all, it began very analog by just sketching down this thing here. And okay, now of course we have to bring this somehow into a computer, and we do this by introducing a coordinate system. I call this now a lattice, a 2D lattice of space-filling tiles. And the tiles, of course, they are these nice little shapes. And I'm pretty sure that this is also the exact shape that Richard Riley has used. It's pretty straightforward. I mean, you have like a 45-degree angles here, and then it's basically just composed of 4 of these simple triangles. And then we put this somehow in the 2D plane. We introduce a coordinate system, and then we can use 2 integer numbers to address all these tiles where they are sitting with respect to each other. And then we also want to somehow interact these tiles. And I will explain in a minute what I mean by interact. But first of all, we also need to know what are actually the neighbors of the tiles, right? So I want to have something to do with the neighbors. Depending on how the neighbors are, they should do something. Now for the upper and lower neighbor, that's really easy, right? I mean, if the tile is I and j, and then you have, say, I is your x direction and j is your y direction, then for the upper and lower neighbor, it's very easy. You just go up 1 step, you go down 1 step, and that's how you get your upper and lower neighbor. Now for the left and right hand neighbor, it's a little bit more complicated because these tiles, they have this odd shape. They're kind of lopsided. And so in order to get the left neighbor here, actually not only have you to go 1 step to the left, but you also have to go actually 2 steps down to get the left neighbor. And conversely, of course, also for the right-hand neighbor, you have to go up 2 steps, and then you get the neighbors. Okay, that's nice, I guess, but so far just gives us the tiles, which then eventually will be filled with colors, hopefully. And now you already know it from my introduction that I'm a physicist. And so, of course, what do physicists do? Well, they come up with some physics model. And again, I just thought about it a little bit, things that I've used in the past in my career as a scientist. And I found this, what is called the Potts model. And it's really just a simple model coming from the study of magnetism. What does simple mean? Well, I guess there is nothing really ever simple is there. But in this context, I think it's simple enough. I mean, basically what you do is you call then these numbers here spins. So you introduce a concept of a spin where then each spin is connected to a tile. So this comes from the study of magnetism. You could think of that as some magnetic domains. But what really is important here is that we assign some numbers to these tiles, right? So we still have our lattice of tiles, and now we assign some numbers to them. These numbers, they're just taken at random. And here in our case, we have now 6 different numbers. So they go from 0 to 5. And then that's kind of our spin state of the physics-based model, so to speak. Now, I've already hinted that the spins will interact with each other in a physical way with their immediate neighbors. So if I have this here, for example, this 5, interaction then means, okay, I have a 5 here and I have a 3 up here, 3 down here, 3 here as well, and the 2, I have 1 here. And then depending on how exactly these numbers look like, some physics will go on. And one further bit of notation, you can then of course write down the full, what we call the system configuration, so the full state of the thing, by just writing down a sequence of numbers again. So we call this kind of the state vector. In our case, this is just a sequence of all the spins. And for the shown example here, this would just be a vector of now length 15, since there are 15 spins on the lattice, and it would contain just the numbers 0, 5, 0, 1, 3, and so on. So it's just telling us what the numbers here actually are. Now comes another concept from physics. I know there are many fancy words, but don't worry too much, because at the end of the day, it's not really that important about the formulas. It's really the ideas and concepts behind which are important. So what we do now is we introduce what's called a Hamiltonian. And this is really just a fancy way of saying that we calculate the potential energy of the whole system, whatever that means. And yeah, it looks kind of frightening, but this is just a mathematical way of writing down a sum over all these neighbors here, basically. So we go over all the places where tiles touch each other, and then we do something, we see something depending on how these numbers are. Now, in this particular case, we have here this delta thing. It's called the Kronecker delta. And what it really does, it just counts if the numbers are the same or if they are not the same. So if they are same, it gives us a contribution of 1. If they're different, it gives us a contribution of 0, so no contribution. And then there's also a minus in front of it, so it makes it negative, basically. If we have two equal numbers touching each other, the energy goes down, gets more and more negative. And if two different numbers are touching each other, there is no contribution, so it's just 0 energy. So for example, these 3 here, touching these other 3, this would give us a contribution of -1, and then we also need some constant here to make it an actual energy. Whereas, for example, this connection here, 3 and 5, this would give us no contribution to the potential energy of the system. Now, this already is a pretty neat concept because we have this huge lattice. Well, it's not huge here, but it can be potentially very large. But now with the potential energy function, with the Hamiltonian, we can reduce it to a single number, just the energy. And that's already pretty important. Of course, now, you know, in real life, potential energy is something which tends to get minimized in some way. I mean, water, for example, it flows down from the mountain all the way to the sea. But the important thing is we can reduce the whole thing to just a single number by using this energy function. Side note, just on this simple lattice here, we have already 470 billion possible configurations, which can be written down like that, which is just 6 to the power of 15. And this already gives us a hint, yeah, we can never see all the configurations. So we will only ever be able to see a small subset of all the configurations because, of course, this grows quite a bit. And so if I make my system just a little bit larger, this will get larger by quite a bit. Now, there's one thing I have not told you so far. And this is, we have said there are 4 neighbors for each of these tiles, for each of the spins. Or there should be 4 neighbors. But then, of course, what's this lonely guy down here? It seems he's very unhappy because he has only 1 neighbor. And that's not good. You know, we want them to be all happy and all have an equal number of neighbors. And, you know, equality is good. So let's have also equality of neighbor numbers for our tiles. And there's a mathematical solution to that. We call this periodic boundary conditions. It's just a fancy, or maybe not so fancy way, an easy way of making sure that everyone has exactly 4 neighbors, up, down, left, right. And if you think you don't know this, well, actually you do know this. Because just think of our world, and let's have for a moment a look at this very stereotypical, almost infamous Mercator projection, where Europe is sitting here just in the middle of the map, and say you are somewhere over here in Japan, and you want to go to California, over here on the US West Coast. And if you're very naive and you have only this map, then you could think, okay, that's a very long way, and I have to go over here, so I have to cross the whole of Asia, I have to cross the whole of Europe, then I have to cross the Atlantic Ocean, then I have to cross the whole of the North American continent before finally arriving in California. But then, of course, we know our world is not like that, and we have kind of periodic boundary conditions on the world as well. And so instead of taking the long way home, we can just go the other route, the shorter route, crossing the Pacific Ocean, and then we go from Japan to California over here. And it's still a long journey, but it's much better than the alternative. And exactly the same we do with the spin lattice. And the only complication now is, in the case of the spin lattice, we also do this with up and down. So when we leave up here, for example, we enter again down here in the bottom. This is something which is not the case for our world because we live on a sphere and not a donut, as far as I'm aware of. But you get the idea, right? It's pretty straightforward at the end of the day. Now, what is then actually the neighbor of this tile? Well, I would say let's just have a look and let's just apply our periodic boundary conditions. Let's look at the 0 guy over here, then go to the left, to the right, and then we enter here again. And I see what you're now thinking. You're now thinking maybe, oh, this is not right. Should be that one probably, no? But it turns out it is right. And actually, this is the correct way of getting the neighbor. And I find this quite fascinating because it immediately brings us back to Bridget Riley's art, where it's also a lot about optical illusions. And it's quite a nice example by just drawing a little bit of those tiles, we immediately get these optical illusions as well. All right, so what have we done? Let's recap for a moment, and I think we are already halfway there. So first of all, we have created a lattice of tiles. Somehow address them with a coordinate system, and using this coordinate system, we also have a way how we can find their neighbors, their immediate neighbors on the lattice. We also know how to calculate the system's total potential energy, or the Hamiltonian, which is really just a fancy way of saying we count how often we have cases where equal spins or equal values are touching each other. And as a bonus, we even do this using periodic boundary conditions, so we have learned something about that along the way as well. And that's all pretty nice, but so far, there's still not that much physics in there, is there? I mean, it's all just numbers and some mathematical concepts, but so far we have no idea whatsoever how this were to behave if it would actually exist in the real world, where we have temperature and all these nasty effects. And to do this, we need one final concept, and this is the study of statistical mechanics. So this is now kind of the last complicated thing I'm going to introduce. So what is statistical mechanics? One of the founding fathers of it was Ludwig Boltzmann, who worked at the University of Vienna, pretty close to here. But before we get into it, just one small word of caution. So there is this kind of famous textbook, States of Matter by David L. Goodstein. And in his very introduction chapter about statistical mechanics, he writes, Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it's our turn to study statistical mechanics. So yeah, take that with a grain of salt, I guess. We will go on regardless. And if you think you don't know statistical mechanics, well, you actually do know statistical mechanics. Because what it really is in its essence is how we can understand the properties of a kind of large-scale system, a large-scale or macroscopic system, in terms of its constituent microscopic parts. So think, for example, of a glass of water, and everybody knows water. We have water everywhere in our life, so that's easy. And macroscopically, it's a liquid, and it's completely continuous. But if you go further down on the molecular level, you will see, okay, water actually consists of literally billions and billions of microscopic water molecules. You might even have some poisonous substance in here, but let's not worry about that too much for now. And so the main concept behind statistical mechanics is how can we understand the macroscopic properties of our substance by just knowing stuff from the microscopic world. So how can we transfer somehow knowledge from the small world to the large world? This is, in essence, what statistical mechanics does. And so it also relates all these quantities. We have the microscopic quantities on the one hand, like also the energy of our spin lattice. And then there are the macroscopic properties like the temperature, like pressure, heat, stuff like that. Now, what does Boltzmann say about this? Well, Boltzmann, he gives us a formula, and I don't want to go too much into details here, but suffice to say, it's about statistics, it's about probability. We have the probability here to find our lattice at some space, or really any physical system. We have our Hamiltonian here again popping up in the function, and we also have the temperature right over there. And here you also see that's pretty nice because now we only can use the temperature and the energy, so it was good to have a way of calculating the energy of the system, and we get somehow a probability function, how likely it is to see one outcome. The bottom line here is there is a relation between temperature and energy. It's just not quite that simple. It's of a statistical nature. So what this means is if we have high temperature, we will also see high energy. But it's not one-to-one, it's only in a statistical sense. So if the temperature is higher, there is a likelihood to find a higher energy. If the temperature is low, we will rather see lower energies. And also it's not a linear relationship. We have this formula here with the exponential, and this is what we call a Boltzmann factor. and all that. And yeah, there is also the Boltzmann constant, which you just need for, let's say, reasons of making the units right, which of course is named after Boltzmann. Now, if you're super clever, you just use an equation like that, you stare at it long enough and have your pen and paper calculation, and you learn everything about the system by just pure mathematics. Unfortunately, I'm not that clever, so I have to use a computer simulation. And so what I have done here in this case is I have employed what is called the Monte Carlo simulation. In this particular case, I'm using the Metropolis Monte Carlo algorithm, and this gives us a way of basically simulating the system, the physical system. In the case now, here we have the spin lattice at different temperatures, at low temperatures, at high temperatures, and everything in between. Now, here we also see Boltzmann doing something similar. So this is a drawing of Boltzmann using an early computer to also perform such a simulation. And you can see this is an older drawing, right? Because I mean, this computer screen, it's almost square. So now we have all these fancy widescreens. So for me, this is already reason enough to believe that this is an authentic picture of Boltzmann doing this kind of simulation work. And then, of course, after we have done the simulation, we just visualize it with the usual suspects, in my case, with Matplotlib. The main core of the simulation is really just this here. So we have our spin lattice at some position. We make a step somewhere, then we see how the energy changes. If the energy goes down, we always say, okay, I just stay here. I like this because energy, it likes to go down in a sense. But then if the energy does not change negatively, if it goes up basically, then we only accept this with a certain probability factor. So we have random numbers coming in, and this probability factor then of course is related to both the energy change as well as the temperature of the system, where again, we know from before already, higher energy, higher temperature also means we are a bit more likely to be good with high energies. Okay, but how does it look like now? Well, it looks a bit like that. So I have done the simulations now for our lattice of tiles, and I have also used some nice color scheme to visualize them. So now, of course, all of the numbers, they are just colors. And I thought, okay, what's really the kind of meaning of temperature in this sense, right? We have high temperature, we have low temperature, we have intermediate temperature. And I thought of it, it's almost a bit like in our solar system, coming back to this initial part about the solar system being eaten up and all. We have different planets in our solar system. So for example, we have Mars. And Mars is kind of here on the left-hand side. It's very cold and barren, and there's not much going on, and you would freeze to death. And you also see this here, that it's pretty uniform, not much going on. I mean, we have a few specks of color popping up here, but that's still pretty boring. And then on the other hand of the spectrum, we have Venus, and Venus is really hot, and it's a hot and violent mess with like 400 degrees or so of surface temperature. It's kind of the situation here where, yeah, there's a lot of energy and it's very violent. It's also kind of dangerous, and in the end, it's also not that exciting, because if the temperature is that high and the energy is that high, it means we have just random chaos, and there is no structure there anymore. It's just a random arrangement of colors, basically. But then, of course, in our solar system, we have this kind of Goldilocks zone of intermediate temperatures where Earth is sitting and where the temperature is just right in between, where the temperature is just right for water to be liquid, just right for life to exist. And in a very similar vein, we have the same for our little lattice of tiles, where there exists a temperature which is just right, intermediate, where all the excitement is going on, and where we have some chaos here, and then we have also these beautifully ordered bits of larger parts of the same color or the same spin. This, of course, is now connected to each other due to periodic boundary conditions. And of course, this is just a snapshot, and I'll show you in a minute that we can also animate this in a bit more interactive way. But I found this quite beautiful, that this kind of almost cosmic, or at least planetary concept of what is a temperature, what is just right, what is too hot, what is too cold, that you also see this in a very cartoonish fashion in our model here. Okay, Now this is the Python conference, PyCon Austria. So I feel obliged to show at least a little bit of Python code. But it's all pretty straightforward. It's just using libraries, and we use NumPy to get our arrays, and we use matplotlib to visualize this and just fill the colors. Two things maybe which are a little bit important, at least for me. First of all, we have a palette table, which gives us colors, really nice colors. So I think colors are important. Brings us directly back to the original artwork. And also animations. Animations in matplotlib, you can totally do them, but it's a little bit cumbersome. So it's not just drawing your plot again and again. That would be way too slow. So you have to do a little bit of trickery by using this animation functionality from matplotlib. So now let's see if this will actually work. The idea is, yes, it does work. You're just not seeing it yet. Perfect. Okay. Let's just, sorry, I'm struggling here a little bit with the mouse. So what you should see here is, yes, now it's working. Here we now have kind of a live simulation, so this is all unscripted. It's working now, fortunately enough. Here we see the temperature, and what is going on is we slowly ramp up the temperature. So we have started with an initial state where it's all just in one direction, where it basically was all just green, and now we are slowly ramping up the temperature. And by doing this, you also see that we have probably already passed the regime of Earth, and we are already now in the kind of hot and violent mess of Venus. And now the system basically has lost all its initial information. It's more or less completely random. Now the temperature is already going down again, and this is actually programmed in such a way that this will loop forever, and I will let it run, and then maybe at the very end we can have a last look at it. One other thing which you might have noticed and which I have not told you so far is we see kind of this streakiness here, where it seems that along the diagonals there's a bit more order than in the other direction. Well, this is very much on purpose. If you look closely at the Hamiltonian, you would have noticed this J factor in there, and this was just a way of giving us a bit more control. Now, what I have done here is more control means the system likes it even more to have equal colors or equal spins aligned along the diagonals, and this is also what we are seeing here. One other aspect, what you see here is now we're all blue, and this is completely at random. I mean, it could not have predicted that. We started with all green, now we're all blue again. The colors, they are all the same. I mean, they have no particular meaning, but what exactly we see, it will be the same. It will be different each time, each and every time. And I can guarantee you with certainty that all these frames, you will never see them again, never ever, because there are just so many different ones that there's just no chance at all that you will ever see the same frame here twice. Okay, now it's ramping up again, and you can probably see now what you should have seen in the beginning when I had some technical problems. It's all very uniform initially, but by ramping up the temperature, eventually we get more and more order. We get more and more chaos, and then this repeats and it goes on, and it pretty much can go on forever. Okay, so we'll now go back to the slides. Yes. Come kind of to my conclusion. What have we learned today? Well, first of all, at least for me, kind of the big take-home point is here. Physics can be fun. It can be exciting. Sometimes it can even be a bit artsy, I guess. I'm not sure, but I think so, for me anyway. And then Python. Why have I used Python? Well, I use Python a lot in my work as a data scientist now and a programmer, but I also like it for little private side projects like that, because it's really a all-in-one tool. You know, we have the simulation aspect, the visualization, even the animation, which we have just seen. And this is all done in one language, and I don't use separate programs for that. I mean, back in the day, I probably would have used a separate program for each of those, especially back in the day when Boltzmann was doing his simulations on the early computer. And the second take-home message is also libraries are really great. So that, of course, immediately ties in with the first one, that we have all these amazing libraries. We have NumPy, we have Matplotlib, they're the usual suspects. Now, I've already hinted you, my favorite package in this project definitely is Palatable, which gives us all these nice colors. It comes from Cynthia Brewer, who is an American geographer and who initially did these colors for coloring maps. It's all open source and you can find it on the website. And I think, yeah, it's really nice to have beautiful colors. Now, at the end of my presentation, we can again ask ourselves the question again, what is this all for anyway? Why were I doing this? Because as we have seen in the XKCD comic also, 4 or 5 billion years from now, the Earth, the inner solar system, Venus, where it's super hot, the Earth, where it's just right for now anyway, never mind global warming, Mars, where it's super cold, it will all be eaten up by the sun turning into a red giant and will be gone. So what's the point of it? And to be perfectly honest, I still have no idea about that. But at the very least, we got some nice pictures out of it, and that's for me already something. Thank you for listening.
How did you come up with this?
What do you mean, how did I come up with this? I mean,
what was the trigger that you experimented with the physics exploration, so to speak?
I mean, I just went to the museum. I found this really exciting to see this kind of shapes, and I thought, you know, maybe there is some connection there to physics and to simulations. And of course, in my career as a scientist, I have done similar work where you have some kind of physical system which is pretty abstract, and then you do a visualization where, you know, of course, the visualization, it's mainly there to drive home a science point and where you want to show something. But then every once in a while, it also is the case that just the pictures that come out of it, they look really nice. And I thought, why not, for once in a change, just do something where really the pictures are the main point? Because normally when you do this, also in my real work, of course, I do a lot of say, creating plots and so on, and maybe you create a lot of fancy, colorful plots to satisfy some bean counter, maybe, I don't know. But there's always some purpose behind it. And I thought, why not for a change do something where the picture itself is actually the purpose? So that was my motivation.
Thanks.